Hi everyone, and welcome back to the Information Bottleneck. And today we have a very special guest, Michael Bronstein, professor of AI at the University of Oxford and the scientific director at AITHYRA. Hi, Michael.
Thanks for the invitation. Great to be here with you.
Hi, Ellen.
Hi again, Ravid. Hi, Michael. It's really a pleasure to have you on our show.
And as always, we'll start with some recent news and cool paper that we have found in the last week. So I think we will start with maybe a very paper that attract a lot of attention, as is more recursive reasoning with tiny networks. So the idea of the paper is that they used really tiny network, 7 million network to do recursive reasoning. And they tried basically to optimize these reasoning in the hidden dimension space if you want, or like if you want, you have X, Z, and Y, and you're trying, X is your input, Z is the hidden variable, and Y is some prediction, and you're trying to optimize Z in a recursive way. So you're doing some iteration over it, and then you're trying to predict Y. And apparently, this model gives very good results on some task, Sudoku, puzzling solving, thing like that. And the internet was like, that's it. We don't need scaling anymore. We can solve with tiny networks. We can solve all of our problems. What do you think about it?
Well, I haven't tried the paper, so I don't want to say something that is uneducated guesses, but I think I would be a little bit careful with the statements that we are done with scaling. So I think if you look at least in the last 15 years or so, scaling really has been the driving power of all deep learning. And every time that we hear that it's running out of steam or running into the wall, we get another maybe even dimension open up, so to say, in which deep learning can be scaled, right? And I think this has happened relatively recently with all the inference time scaling. So I wouldn't write it off immediately, but I think it's interesting that people are probably looking beyond huge transformers. What could be the next model that could work well? I think whether it can work well across the board and in different situations, or is it some sort of one example that works in one case and doesn't work anywhere else? I think that's yet to be seen.
I'll quickly compare this to the previous, I think, flavor of the month paper, which was Laura Without Regret, which I think before that was the one about determinism, right? Just for those who remember any of the history of the last few weeks. But we see so many examples of, claims of get 80 or 90% of something for only 10 or 20% or even less of the cost in machine learning. This happens everywhere. And happens with parameter efficient fine tuning, inference time scaling as we're seeing now. And I think that there might be an absolute sense where this is true in many cases. But marginally, this is almost never the case, which is to say that every one additional IQ point that we add on top of like GPT-5, and I'm aware that IQ maybe isn't perfect for here, but just something analogous to raw intellectual strength, is worth, I claim, quadratic or exponentially increasing returns, like rate of returns. So even if there was like truth to the kind of the base statement that they make about scaling in here, which is, for those who don't know, the authors wrote a bit of a blurb that says, hey, a whole lot of research labs are dumping a lot of money in, and I had no money and resources, and look what I was able to do, and kind of trying to point at them and laugh a little bit. But my response to you is to be like, imagine what you could have done, poor person, rallying against scaling if you had those resources and knew how to leverage them. So I would say we should, just as Michael is saying here, we should not try to devalue the power of scaling.
Yeah, I agree. I think so I'm a big fan of I don't know, hidden variables, and like it's even like JEPA style training and all these things. And I think like if we want to get to the next level, we should use them, and we should do like I don't know, optimization in the representation space and all these like self evolving training and things like that. But I also think that at the end, for most of the use cases, you don't need general purpose model that can solve everything. You need something very specific and that can solve 1, 2, 3 problems. That's it. And I think this line of research can be a great example how to do it. So it can be take like one line of research is like, yeah, let's take a ginormous transformers and distill it or compress it or whatever. But another approach is to do something like that. The question at the end, if it will work in, with more data and other domains, and like when you need more sophisticated capabilities and to solve more complicated problems. But I don't see a problem if a model can solve only one thing and that's it.
Yeah, I think there is a little bit of hype of foundation models, and we see it also in the field of, let's say, biology, right? So that's where people try to make these gigantomaniac models and say that now we solve all biology with one model. But when you talk about specific applications and you compare them to sometimes even embarrassingly simple baselines like linear regression, right, or maybe random forest, then they can barely outperform by fractions of percent, if not even working worse. So I agree in this sense that sometimes small models that are purpose-built are better than more sophisticated and hyped models. So yeah, but again, I think it's a delicate balance, and in some applications where we've seen the power of scaling, just because some small model can perform well in one application doesn't mean that these models should cease to exist.
And I want to quickly mention I've been returning back to what feels like a relic of the 2020 to 2022 era of machine learning, which is AutoML, and kind of helping a client of mine who needs an AutoML deployment on stock prediction of all things. And so I don't know much about time series, but what I can tell you is AutoGluon, at least, which is Amazon's AutoML solution, as of the last few years, is throwing tabular data set foundation models at everybody and trying to use those as kind of the primary thing that they rely on, rather than, the traditional baseline of logistic regression, XGBoost, and kind of going from there with more compute. I'm extremely worried about this, especially because I remember all the, hype about profit back in the day, that model from Facebook, and what ended up happening there with, people realizing it's not great, and things like what you mentioned, linear regressions and ARIMA and all these were beating it. So I'm especially worried right now that the race to foundation models may have horribly damaged some of these fields, even to the point where in some cases they could be behind where they are, or at least in sub aspects of certain fields, like parts of biology, where they over rely on fundamentally untrustworthy and not well calibrated foundation models.
But why you think so? I think it's an interesting question. Why we don't see like good foundational models in other domains, right, besides vision and text? My take is that, right, everyone, as you said, everyone wants to make a foundation model for tabular data, but I think in the end, tabular data is just like a general name for we want to solve everything, and we want to solve like all kinds of problems. So it's kind of like no free lunch, right? Like you can't learn everything. You can't learn everything, and you can generalize for all the different things that in the world. So I don't know, like you need to solve, like if you want to make foundational model for something specific, you need to take data for this type, but you can't solve it in the general case for tabular data.
I mean, I would say that one of the reasons why you would like to have foundation models for tabular data is by far probably the most prominent kind of data that you see, especially across different businesses, and especially businesses that are kind of old tech, where where you have records from 50 years ago that were even manually fed into some database, right? And you don't have maybe more sophisticated or cooler types of data like graphs, right? So, well, we actually are working on, and we have a paper recently on basically formulating graph neural networks using foundational tabular models. So this is also an interesting direction. But I think they're useful potentially if these models work, right? And we have some examples that they seem to be working. They would be useful immediately across a very broad range of applications.
So you think like we will see with true foundational models for tabular data in the next years?
We see already now, at least papers that make these claims. Again, I would be a little bit careful because I think the variety of use cases here, it can be huge. And I'm not sure that we have actually a very good way of evaluating them and to say that is it really a foundation model or is it just, again, a good result on a couple of use cases.
We need a minimum. So I'm going to deploy a few statistical concepts real quick that probably you two know a lot about, but I would encourage anybody else who's listening and isn't aware of to Google these. One of them is Simpson's paradox. The other one, oh god, I'm forgetting the name. Basically, it's like 4 monsters or something. There's like data sets that are constructed to be totally different, but have exactly the same like mean, median, mode, standard deviation.
Oh yeah, the one with the dinosaur, right? So
Yeah. There's and actually there's expansions of that paper where now people have written software where they can automatically create like any data set, like large number of data sets for like 10 or 20 properties all held the same for that data set, which is crazy. Or you can even like draw whatever stuff you want where they all have that same property. I've seen expansions of that paper. The point of this is, well, I'm going to compare another thing too simultaneously. GPT-3 was super exciting circa 2022, but it wasn't instruction fine-tuned yet. So that wasn't the Chat GPT moment. Chat GPT moment's 3.5. That's where the world went into overdrive, right? We don't have, and also, people in that tabular foundation model world can correct me here, but the 3 foundation models that AutoGluon had that it was trying to use didn't have instruction following as part of it. So at a minimum, I need to be able to give it my data and tell it about my data in maybe natural language, right? Where I can tell it, hey, this is like about pirates or something, right? Because otherwise, what those foundation models are basically trying to do is look into their approximate retrieval weights, basically, and find the most comparable, I guess, combination, right? Or in maybe the geometric, way that you look at things is probably a better way to even describe this stuff, right? But it's trying to retrieve, making predictions based on how these previous data sets operated. And that's based on the assumption that data sets that look the same, reflect the same underlying phenomena in some way, right? Which I think is totally false, right? Like, and that whole thing of like correlation without causation and humorous stuff online about like, you can predict the number of pirates in the world with like the consumption of like potato chips or something, right? Where it's total nonsense, but the data looks the same, right? And it correlates really highly with each other for some reason. That's why I think we need instruction following in a foundation model for tabular data, and probably a lot more than that.
Yeah, I think there are several attempts to do it already, right? Like to include the text and to explanation how the data look like and what does it mean the data, different parts of the data, different fields, and to incorporate into the model. Again, I don't know. I didn't see something that that like is really good and you can say, okay, like it replaces, right? Like now if I have tabular data now that I don't know anything about it, or like I know something about it, but now I want something like very quick and dirty, I will use I don't know, XGBoost or CatBoost or something like that, right? Like this is the go-to for many different applications in different companies, right? And I don't think we are in this level or this stage that we can say, okay, let's take another model and just tell him what is the data and things like that. It's difficult. And I don't know if we will see it. Maybe. And maybe we'll see it. But I think how to use prior knowledge in your model, it's maybe the most or like one of the most fundamental questions that we have here. Or like, I don't know, several months ago I saw a work, I don't remember the name, but they looked on time series data and they just asked a language model to give prediction. And it was of course really bad, but when they use VLMs and they actually use the figures themselves, so they just print the figures, right? Like they print the time series values. They show that this is actually like it improves the model by a lot. And all like these small things that like you add X labels and Y labels and you scale it differently and things like that actually improves the model. And of course, this is a way to insert prior knowledge, right? Like you tell the model that now this is a time series data and it behaves like that. And so it can integrate or like use other time series data sets and it knows that like this is smooth or something like that. So how we are going to do it in the general case, I don't know, maybe there is no good solution for it, but I think it would be the big challenge for many different labs and companies.
I agree. Well, maybe regarding Tabora Foundation models, might want to talk to Yuri Leskowitz, so their startup Kumo. At least to my understanding, I haven't followed them very closely, but that's what they're doing. They of course they worked on relational methods and graph neural networks, but I think most of their data and most of their clients have tables, what everybody has. And yeah, so regarding your comment on LLM, so I've seen a couple of years ago already, there was a paper about using LLMs to solve differential equations. So you can
And it
do
didn't
even
work.
that. No, I think it works.
It works.
I'm not sure you can guarantee. So that's where actually providing some description of what you expect, right? So some sort of rules is very important, right? Because in differential equations, often you have certain expectations about the nature of the solution, right? So you have some physical principles that you don't want to violate, right? And of course, an LLM without these instructions won't necessarily be able to do it.
Yeah, I think it's interesting because like there are different levels that you can actually look on. Like when you want that the LLM will solve something that is not directly related to language, you can also look on the representation, right? And actually, I just saw a paper that so the name of the paper is LLMs Reproduce Human Forecast Intent by Semantic Similarity Hallucination of Flickered Ratings. And so the idea, people have tried to ask LLM to reproduce, some survey results or what will happen when you ask people, like, you will buy this product if I will change the color from yellow to orange, or like, what do you think about the decision of this politician or something like that? And they try actually to see if the LLM will mimic the result of actual humans. And apparently LLMs are really bad in these types of questions. But in this paper, what they actually looked, so they looked on the representation. And they tried basically they cluster the representation and they extract the actual result from the representation. They ask the question, and then they look on the representation and they put another, you can say, decoder on the top of this representation. And it works much better if you do it, and you can play and you can condition on different demographic settings and demographic properties, and it will mimic the actual human behavior. And I think this is very interesting because it looks that different resolution, if you want, will require different layers, right? Like you don't always need the final layer in order to get your I don't know, the solution for your task. Yeah, this is it's actually related to a paper that me and Michael will participate recently about what is the optimal layer for different tasks, like how you connect the task to what layer you actually want to get this the representation for this task.
I'll just quickly point out that figuring out at decoding time the correct place to exit and maybe early exit is so good in so many ways. Like, first of all, less inference cost, right, if you're early exiting. Second of all, if you're doing it right, hopefully it's more accurate for that token or part of the solution space you're looking for. But finally, people have been recommending this for a long time. Stable Diffusion XL came out with clip skip equals 2 by default, which means that they actually want you to exit out on the second to last layer. And so everybody does. Nobody uses the last layer on Stable Diffusion XL. And that was like 2023. This idea is somewhat old in a lot of ways, probably the whole predating, many of all these papers, but kind of the results of papers themselves are showing, that it's very smart to do this. And yet today, ChatGPT, Claude, Gemini, most of the local models, the mixture of expert models, I think, are a bit different here, but the dense models aren't doing this at all. And they probably should start to figure out a theory of this for everybody's sake.
I don't know if we think about, when you say theory, I don't think we actually mean the same thing, right? There are no equations in this theory, right?
Yeah. I mean, Of course, I mean like an empirical understanding, not a theory. Yeah, you're right.
I don't think that anything that, or almost anything that exists and is presented as theory of in this field would actually count as theory for people who do theory, right?
Yeah, so like okay, so I want to ask you about theory and like and AI these days. What do you think, right? Like, as someone with a theoretical background, what do you think is the do you see I don't know, a path the theory is actually meaningful in the field?
I don't think that there is the theory. So we have probably multiple viewpoints, and people basically come with their viewpoint and might provide some intuition. So I don't think that there is really good theoretical or single theoretical understanding of the field. So I've seen some interesting takes from AITHYRA. So it has this information theoretical approach to transformers in particular and to LLMs. I mean, we've been working on geometric approaches to deep learning. And again, it's not theory of AI by any means, but at least it's something that maybe allows you to make more disciplined choices in deep learning architectures. And it's been useful in several fields, but I don't think that it counts as a theory of deep learning, right? So it allows you to derive some architectures from first principles, but it doesn't necessarily explain how they work.
So do you think there is like, I don't know, when you work, you look, okay, let's think about general, like what we actually want from first principles, right? And from our network or from our model. And then you start to think about the solutions, or these explanations are in a retrospective. And yeah, like we have model that worked, so we can use some tools in order to explain why it works.
Well, it's always, I think it's because it's an engineering field and it's driven by applications. I think it's always that a model that works, then people try to explain why it works. It often happens that you have good empirical results, but not necessarily a deep theoretical understanding. And people who can provide a deep theoretical understanding probably even want to look at a certain model because it works well, right? So that's also, deep learning has not been really interesting for mathematicians before it started delivering. And then many people wanted to understand why it works. So I think, to me at least, I know that it's old news, right? But for example, Van Malai and Joan Bruna had this beautiful series of works explaining why convolutional neural networks work from first principles. That was already probably almost 15 years ago. I think Stefan in particular got interested in deep learning when it started delivering results.
And do you think geometric deep learning, or to look on deep learning from geometric perspective and I don't know, graphs, neural networks and things like that, can give you such a explanation?
I mean, geometric deep learning. So some of the ideas that we've been, I think, exploiting in the last years have been around for quite a while, right? So I don't know if you've actually read the book Perceptrons by Minsky and Papert. So it's always, no, okay. So that's probably like everybody else. So people always have opinions, and actually strong opinions about this book, right? So in the legendarium of the AI, it is made responsible for the onset of the first AI winter, right? That killed neural networks for many years. And that was late 60s, right? So 67, if I remember correctly, when it was published. But it's interesting that what they called perceptrons is not exactly what Rosenblatt called perceptrons, right? So it was really the first geometric attempt to look at problems of pattern recognition and what was called machine learning or AI at that time. And actually it was subtitled An Introduction to Computational Geometry. And nowadays, computational geometry is something that is a flourishing field, right? And we have conferences, we have journals, we have papers published in this field. But at that time, it was something that they made up. And people were even commenting about this. Will it become an interesting mathematical discipline, or will it just peter out somehow? And one of the things that they introduced in the book was basically group invariance theorem. So looking at neural networks and looking how they map orbits of a group to the outputs. And it was mainly an analysis tool rather than some kind of principle to design new architectures. But I think these ideas go back at least as early to this time, and probably also late 80s. It has never been really exploited properly. And I think in the last probably 7-8 years, we've seen the main enthusiasm about it. And probably the biggest success of the geometric approaches was obviously AlphaFold 2, which got the Nobel Prize in chemistry, right? So you can call it the triumph of geometric deep learning.
So yeah, maybe let's start like what does it mean actually geometric deep learning and why like you think it's a good approach to look on different problems.
Yeah. So if you think of, well, in general, how machine learning problems work. So you start with some data, right? So that typically is assumed to be represented as a vector in high dimensional space, right? And then you run it through some layers of a neural network and you produce some output, right? So let's say, I don't know, take an images of cats and dogs, right? And you want maybe a simple, this canonical example to produce a binary classification, right? Who is a cat and who is a dog. Now, machine learning problems suffer from the curse of dimensionality. So if you approach it from the perspective of approximation theory, right? So even among continuous functions, right? Or even if you have stronger regularity properties, the number of samples that you will need to take will depend exponentially on the dimension, right? So even very modestly sized images of, I don't know, m nis digits, almost 1,000 dimensional. So in theory, the number of training examples you will need to show to this neural network will be not only bigger than the number of the population of cats and dogs on Earth, more than the number of all organisms that live, more than the US national debt, more than the number of particles in the universe, right? So more or less any astronomical number, right? So it doesn't really work. So the idea of geometric deep learning is that you move away from these simple notions of regularity towards what we call geometric regularity. And you need to assume that there is some kind of underlying geometric structure to your data. So in case of images, for example, these are functions that live on some geometric domain, right? So plane or a grid. And you can define the structure of this domain by an action of some group. For example, the group of translations. So roughly, I have a way to say that I can move things around in my image and I don't want to care where a cat or a dog is located in an image, right? As long as it's a cat or a dog, I want to be able to say it, right? So in the traditional architectures, I will need to show examples of translated cats and dogs in order for the neural network to learn it from the data, right? And we do it all the time with data augmentation, right? But in the case of geometric architecture, you want to design your neural network in such a way that it will be, for example, invariant to translations. This allows you to, so that's exactly the group invariance theorem that I mentioned from the book of Minsky and Papert. So if you design your architecture in this way, you can guarantee that all the transformations of the input by the translation group that acts on it will be mapped to the same output, to the same label, right? So I need to show just one example and then everything else will be consistently mapped, right? In the simple case, that this is what you benefit from invariance. You're more data efficient. And you can also guarantee that certain property that sometimes is desirable in your application. Basically, you achieve it by construction.
So just real quick, I'm aware a big part of how people, at least in image space, would try to implement that invariance in the weights was by taking their data set of images and cropping, rotating, flipping, all that kind of stuff. So that way, hopefully, you would train at the data level the model to behave that way. But does that make it geometric just by doing that kind of data augmentation? It sounds like it's something properly at the model level, right?
Yeah. So it's an interesting question, right? So if you look at problems in computer vision, so what sort of invariance do you need there? So it's definitely more than translations, right? So you want some, I don't know. If you just talk about geometric transformations, so you definitely have rotations. In many cases, you have perspective transformations, right? So it might not even be a group. So what we see is that it's easy to implement invariance to some transformations, and it's hard to implement invariance to other transformations. So convolutional neural networks became popular, right? There is nothing special about translations. It's just that they map very naturally to. Initially, it was digital signal processors, right? That can just take two vectors, multiply them, and then sum them up, right? The multiply accumulate operation. So the one that Jan LeCun was working on in the 80s could do it, I think, 120 million times per second. So it was the impressive architecture of that time, right? Nowadays, of course, it's GPUs. So there is this phenomenon that is called the hardware lottery. So it's not that an idea is necessarily better than another idea. It's that it is easy to implement it on the hardware. And this is always somehow sits in the background, and we discuss algorithms, right? So transformers are great, right? And they're better than, I don't know, than some other architectures. But there is nothing really particularly special about transformers, at least in my opinion, right? So some people might have different views. It's that it is easy to implement on the GPU. And if you think of transformers, right, we can talk about it in more details, but transformers are graph neural networks, right? Graph neural networks, if again we look at them from the perspective from this geometric perspective, the symmetry that they implement is permutation symmetry. And transformers, at least initially, have been prominent in language applications and probably in language, right? So the permutation symmetry is the last thing that you want to have, right? So if you scramble words in a sentence, it will produce completely meaningless results, right? So, and you need to work hard. You need to break actually this symmetry by introducing positional encoding, right? So, and again, why then we have transformers that mathematically do not make sense for these applications is because of hardware.
Can you map transformers to graphs? How you're doing this?
So transformers are graph neural networks fully connected on a complete graph with positional encoding. So the positional encoding allows you to distinguish between different nodes that in a typical graph neural network will be, you will not have a way to tell that what is the order of the nodes in the graph.
Yeah, I just want to quickly go back to some phrases you used. Silicon lottery, the way you used it, it's fascinating. I did not even realize that existed. Or I mean, I guess I'm aware of that kind of concept, but I'll talk about that in a moment. There's another silicon lottery that we at, workers at Intel and those who buy GPUs and care about racing them know about. Basically, for a high-end CPU or GPU, you can get as large as, in some cases, 10% performance variance just by getting lucky and getting a slightly better version of it. And so this is a big thing the overclocking community cares about. But the other thing I was going to claim is it never even seemed to me that the transformer model was uniquely easier to run on GPU than other models. For example, random forests, XGBoost, that entire type of models are extremely easy to parallelize on GPUs, and people have. And also gradient-free optimization methods, so like genetic algorithms and variants of those. I actually worked on that as like the first thing I kind of built to learn about machine learning because I didn't know how to do certainly not auto differentiation, right? And I wasn't great at calculus. And I accidentally found a Schmidhuber paper from 2010 that I re-implemented, not knowing who Schmidhuber was, on cooperative coevolution. And it was crazy good even on a CPU, right? I think it's more that there was all this mind share on the transformer and really good results with it. But I'm still waiting for somebody to go and make a proper LLM with a really large random forest and create like a theory of sampling at the token level from a random forest or something. And then now it would be eventually interpretable in the sense of if you had time, right, and wrote the tools for it, you'd be able to get like perfect interpretability of why the model did something. And so I'm just curious as to your thoughts on all of this, right? And also, I guess, this is more engaging with the type of silicon lottery you were talking about, right?
Yeah. So I again, I don't know what is, and I don't remember the specific numbers I heard from NVIDIA regarding complete graphs versus sparse graphs, right? So I think if it's above just a few single-digit % of non-zeros in a matrix where it makes sense to implement it as a dense matrix multiplication rather than a sparse matrix multiplication. In this sense, neural networks, right, considering them as a graph, doesn't offer much advantage in many cases on a GPU from the implementation standpoint. And it's somehow the fact that we have, almost a monopoly of NVIDIA, basically it somehow guides the natural selection of algorithms, right? So you, of course, can come up with algorithms that could be maybe mathematically smart and appealing, but if you cannot implement it efficiently on the GPU, then forget about it, right? And we've seen it also with geometric architectures. So we have all these beautiful ideas about all sorts of equivariant and invariant architectures that, for example, you can implement invariance to more interesting groups, right? Like including rotations. So this appears to be quite difficult to implement on a GPU, and these architectures have not really been very popular. Again, I don't want to disparage any other works. I think there is some interesting stuff, and this is definitely used in chemistry, for example, but not everything that looks correct on paper is necessarily efficiently implementable on a GPU, and that's probably one of the main reasons why we don't see the success of these algorithms, unless the algorithm is not being good. So it's always this combination, and I think we somehow always forget about.
I have two questions. So one is that, like, then you talked about augmentations and like how augmentation, like in some way, like induce invariance or equivariance, right? But we see in the recent years that, like, at least in vision and in text, like we are moving away from augmentations, and it looks at like augmentations are not so important as we thought. But 5-6 years ago, we thought that like, oh, these are very important part, right? Like how to do the exact augmentation. Like there were so many papers about like learning augmentations and what the effect of augmentations. And it looks that we are quite of moving away from augmentations to more, let's say, natural things and or like masking and things like that. And the second question that maybe related to this is that like the world, like you don't have at the end, or for most of the problems, you don't have like a strict invariance, right? Or even equal variance, right? Like you don't have it. And maybe like how can you get this in a more soft way?
Yeah, no, this is a very good question. So you asked actually many things, right? So probably my answer will be long, but bear with me. So first of all, about augmentation, right? So somehow almost in this community of group theoretical approach to machine learning, right? Geometric deep learning, it's almost a bad word, right? So data augmentation, right? So what is that? If you look at it, it's a pragmatic choice, right? So in problems like vision, again, as I mentioned, basically the real transformations that images undergo are not even necessarily modeled as a group, right? So what do you do, right? And maybe some groups are more difficult to implement on a GPU than others. So the choice is pragmatic. So you have a trade-off, something that you can model easily, like translations, and everything that you cannot model, you just show examples, right, by data augmentation. And this is how, for example, AlexNet was trained, right? So it was a convolutional neural network, right, which has translation equivariance, and then you also had data augmentation that tried to imitate how images look like, right, when they undergo natural transformations. This was also the case in AlphaFold, right? So AlphaFold 2 used an equivariant transformer, so basically rotations, but AlphaFold 3 already moved away from it. So it was a general architecture where basically there was data augmentation, right? So you simulate the let's say, different rotations, right, that the molecule can undergo. It's a good question how far you can stretch it. So even works, for example, when you don't know a priori what is the symmetry group that you're dealing with, right? So there are works that try to learn the symmetry from the data or from the problem. I would say that probably bigger groups, right? Big in the sense that if they're continuous, it's the dimension, or if they're discrete, then it's the size of the cardinality of the group, right? Like its permutations is probably very difficult, if not impossible, to learn. And I think there is no way that we can learn, for example, permutations, right? So that's why we work with something like GNNs, which is you incorporate this symmetry, but some smaller things like 2-dimensional, 3-dimensional rotations, you can definitely learn through data augmentation. Now, there is another interesting story, right? And we can talk about it as well, right? So which is approximate equivariance, right? So my favorite example of why equivariance might be a bad idea is motion capture. So in motion capture, it's one of the problems in computer vision. You have positions of 3-dimensional positions of joints on the human body, right? And you basically, when the human moves, you track the positions of the joints, and you try to classify, for example, what kind of motion is going on, right? So the gait, whether the person is running, walking, jumping, and so on. So you would say that here you have the usual O3 or SE3 invariance, right? So the special orthogonal group or special Euclidean group, right? So rotations or rotations with translations. But this is not the case, right? So we don't, for example, see anybody jumping from the ceiling, right? Or jumping sideways. So there is gravity. So this assumption is an overkill. So you never see these kind of examples in your data, and therefore basically you're hardwiring a wrong model into your architecture. So we had a paper with one of my students. So he was actually one of the first, Ahmed El-Haj. So he had a paper with people from Apple in his internship that showed, probably it was one of the first examples of molecular conformers. So a problem in chemistry where they showed convincingly that you don't need an equivariant architecture, just brute force general transformer model with more data, with data augmentation works better. And so it's a good way to start your PhD when you say that everything that your advisor has been working in the past years is nonsense. But we had a follow-up paper where we show that exactly in this case, like motion capture and other examples, if you do not impose any equivariance or you hardwire the equivariance, you don't necessarily get the best performance. So there is some kind of sweet spot, and you can impose equivariance in an approximate way where you get the best performance.
And what do you think, like, where is this spot? Like, what is the factors that affect this sweet spot? Like, do you think this is like, as we have more and more data, we need less and less regularization or like prior knowledge about the architecture, or you think like this is related to the domain or like to things that we don't know yet?
I mean, it's difficult to say something conclusive, right? Because it depends on the problem. So in some problems, you know that invariance is there, right? So especially problems in science where basically this symmetry comes from some conservation laws, right? So these are the laws of physics. So that's how the universe works. In some other applications, this is just our best approximation of the problem. And we know that in reality, it's more complicated. It's just something that we can easily describe and model. But one thing that you don't need to forget is also the training itself, right? So it might be more difficult to train architectures which have these special architecture that imposes hardwired invariance. And it might be easier just to start with a general transformer and then impose it, for example, gradually during training, or impose it as a penalty, or impose it in some other ways. So again, the training part is also often not accounted for, right? So you say that my architecture is invariant, but great, but how do you actually train it?
Are there like methods that you actually start with very strict architecture constraints and relax it during the training as you kind of see more and more data and things like that?
I think you usually start the other way around. You start with a generic architecture and you try to make it more equivariant. Yeah, but I haven't seen any theory really on what is the right thing to do.
I was just going to quickly mention there was before the ChatGPT era, there was a technique for neural networks that involved using genetic algorithms to change their architecture to try to get them to be more accurate. And it was kind of a big deal at the time. The
You
other,
mean neural architecture search, right?
yes, that one, yeah. And the other thing that I keep thinking about with especially with the discussion of rotations, I'm aware that you're talking about like full on rotations of the whole image or figure. But there's a quite famous Interpol investigation that happened, I think, like 15 years ago about a guy who was known as, and you can Google this, Mr. Swirl Face, and it's a heartbreaking story. It's a horrible, like, child predator kind of person who was posting images of themselves and was using a swirl function in some, like, paint app or something to blur their face. But the swirl that they used was like a mathematical operation that could be easily reversed. And finally, they did, like somebody successfully figured out the correct way to reverse the swirl and found his face, and they were able to do a whole worldwide like investigation and bring this person to justice. And so they, last I checked, were in jail. But so this is, I'm curious, first of all, two things. One, how do local transformations on an image, like I guess for some aspects for like classification and facial recognition, we probably, assuming a good usage of this technology, right, we probably do want to be able to recover somebody's face even if the image of it is corrupted in some mathematically regular way. But then second, I would just ask if what the social, given that what I've talked about is an extreme example of like a social implication of something that's close to what we're talking about, I'm curious, what do you see from your side on like the social implications? You've already talked a little about this, but I'm just curious as to more the implications of like geometric deep learning and the questions that you brought up around invariance and etc.
Well, it's a little bit hard to talk about social implications, right, in general, and this is probably some kind of exotic case that I never heard before. So mathematically, something like swirl is a diffeomorphism, right? So it's some kind of smooth deformation, and it sits somewhere between these kind of global transformations like rotation and completely random permutation of pixels in an image. So permutation group is very large, and then, for example, the rotation group is very small, right? So basically, it's a subset of all the permutations that somehow consistently rotate, and then swirl sits somewhere in the middle, right? So how to model it properly, whether you can design an architecture that will be invariant to swirl. Probably in theory it's possible. In practice, I don't see why one would like to do it, right? And then of course there is a question how to efficiently implement it. Yeah, but social implications, I mean, machine learning in general might have social implications. So graph neural networks, for example, that are used in recommender systems. So this is what all the toxic stuff that feeds into our timelines on Facebook or on Twitter. So I guess basically this technology is somehow used, but I don't think that it's anything specifically geometric that is responsible for it.
I have a different question. Like, so we talked about like at the end for geometric deep learning, you assume something about the data and about the type of data that you actually want to learn and the type of the solution or the thing that you want to extract from this data.
Yeah, data and problem. because you can have the same data but different problems, and the assumptions might be different in these
right.
cases.
So can you try to tell us a bit about these assumptions and like what you actually need in order to have like learning algorithm or like a good model? What are the assumptions that you need for your data and your problems?
Yeah, so in some cases the assumptions are obvious, right? So let's say that I give you a set, right? So in a set, a set can be something like 3D point cloud, right? So one of the basic properties of a set is that you don't really have a natural order of its elements, right? So I cannot say which point in my point cloud is first, which one is second, and so on. So I need an architecture that by design need to be oblivious to this ordering. Same thing with the graph, right? So on a graph, of course, there are some situations where you can order the nodes of the graph, but in general, you cannot, right? So if you have, I don't know, a social network, so who is the first user, who is the second? So any such ordering will be arbitrary, right? So you need to be able to deal with it, right? So this is what is called permutation invariance. And basically you build an architecture that implements these principle. In some other applications, it depends, right? So if you think of computer vision, let's say that I have a self-driving car that looks at needs to recognize traffic signs, right? So probably the only thing that I'm interested in this application is where the sign is located in the image, right? So some sort of translational symmetry and maybe also zoom, right? So how far it is. It's very unlikely that I will see rotated signs, right? Unless, of course, you have an accident and the car flips over. But if it's, for example, let's say, I don't know, maybe in near future we'll have flying cars, rotations already would be possible, right? So it's the same problem, but in different contexts, you might have different symmetry. But in none of these cases, we will see any reflections, right? Because it's not physical. But if, on the other hand, you have computer vision problem, for example, I don't know, classifying histopathological images, right? So you have examples of tissues that you put under the microscope and you want to tell whether there is a cancer tumor in your sample or not. You can actually flip the sample under your microscope. So you're interested in both translations, rotations, and reflections. So what kind of symmetry you need in your problem depends on very much on the problem, right? And again, we are talking about exactly the same setting, right? In terms of the kind of data, right? So in all cases, we have images, but what kind of symmetry to assume is not defined a priori by the data itself. It's a combination of data and problem.
And do you think like physical signals are more aligned with these kind of assumptions than text or something like that?
So I think problems in science, in physics, so there is this fundamental result, Noether's theorem in physics, where you can attribute certain conservation laws to symmetries, right? So you can argue that all physics actually stems from symmetry for these reasons, right? I think it was Anderson, Nobel laureate, that said that physics is the study of symmetry. So all the standard model, so that's all the particle physics that we know nowadays can be derived from different symmetry groups, symmetries of the space-time and symmetries of the quantum fields, right? That gives rise to different forces. Yeah. So in these cases, symmetries come from the laws of nature themselves, right? And you know that to get the right solution, you need to impose this, right? Sometimes it might be difficult, and you might compromise, right? Maybe you impose something that is easier to model, and you do data augmentation. But in some other fields, you have no idea what the symmetry is, right? So take a biological system. We don't have an equation of a cell. How do you model it? So what is the right symmetry? So it's hard to say. Now, there are generalizations of group theory or notions of invariance to very abstract notions using category theory. There has been some interesting work, including from my collaborators like Petra Velichkovic from DeepMind. There is even a startup here in the UK called Symbolica. Again, sounds like an interesting thing, but I think yet to be shown whether you can do something that goes beyond the usual means, right? Because when you actually implement it, right? So it boils down to an actual architecture that it provides, and whether you can arrive at the same results without involving category theory is a good question.
And do you think so? There is now a lot of new like simulation models, generative models that can like simulate different aspects of the wall, like they actually keep track the states of the wall and things like that. Do you think it would be helpful in the sense that like the generative process? So it would be easier like to apply like some groups and symmetry groups and things like that?
Well, definitely. So, and there are versions of generative models, flow matching in particular. That's what we worked on, which work in these geometric settings. So one example is, for example, in protein generation, right? So you can think of protein as, so it's basically, well, if probably for the listeners, I need to explain what a protein is, right? So it's for computer scientists. So it's a chain of small building blocks called amino acids. And I don't know if probably everybody played with this toy in their childhood, the snake, right? So you have this kind of linear thing, right? One-dimensional object, and you can twist it in many different ways, and you can more or less fold it into any structure. So that's how proteins work, right? So if you think of it geometrically, you have a sequence of transformations, rotations of one amino acid with respect to each other, which you apply in sequence. And you can generate proteins by deciding how different amino acids will be rotating with respect to each other. So if you think of it from geometric perspective, so this is a product of groups, right? So S or SE and the special orthogonal group or the special Euclidean group, right? So that the relative positions of the amino acids with respect to each other. And you can design a generative model that basically generates data on this exotic manifold, on the product of these rotation groups.
And does it help like to learn better? Because I'm assuming that like there are a lot of states that are irrelevant, right? So you need to understand like which one are actually like actual proteins.
True. Well, of course. So that's what, and you can incorporate more control. So this paper, so we did it with a startup that was doing protein design, Dreamfold, last year, and we had actually two versions. So one was you could do more control, so you could also use, for example, the sequence information for the sequence of amino acids of the protein. I would say that the field again has moved away from these methods, and now what is in fashion are all atom models, where you don't only look at the backbone of the protein, but you basically have everything. So, and then you don't really impose invariance in an explicit way. Again, I think this is more a general trend. What is interesting is that when we talk about geometric architectures, right, geometric deep learning, so all the efforts have been on trying to understand how the transformation of the input should be incorporated in the architecture, right? So roughly the idea was that I know how my input transforms, right? So I want the neural network to somehow interact with the group that describes these transformations, right? So I want it to be translation invariant, rotation invariant, right? Or equivariant, or whatever the group is. But this is only half of the story, because a neural network is a function of two inputs, right? So we have the input, image, sequence, graph, whatever it is. But we also have the parameters, the weights of the neural network. And there we can also have transformations, right? And this has been known for ages, right? So this is one of the reasons why these are non-convex problems. So it was always considered as a hindrance, right? So if you look at the loss landscape, it has multiple local minima, right? And this is because, for example, you can permute the neurons in your hidden layers, and functionally the neural network does the same. So until recently, it has never been exploited in a principled way. So it was always considered as a kind of undesirable thing, right? But it is actually, so there are interesting symmetries in the spaces of weights, and they are not only discrete, it's actually a combination of continuous and discrete transformations. And you can build models that account for these. This is especially interesting because nowadays we're in a situation where we can design neural networks that can take other neural networks as input. We have millions of, for example, LLMs in Hugging Face with some metadata. So so you have the weights of a neural network, and you have, for example, results of its performance on different data sets, right? So this can be used as training data. And you can train neural networks that are significantly smaller, that needs to account also for some geometry of the space of parameters. So weight space learning has become, I would say, a growing field in machine learning. That potentially can change dramatically the way that we train neural networks.
But do you think they actually lies in very, I don't know, low dimensional space? Because like we talked about it before, that like the input should lie in some, like you have some very organized structure, right? Like geometrical structure. But do you think also models and weights are actually have this, or like other different structure?
Well, some models do, right? So it depends, of course, on the model. So probably a good example is low rank adapters, right? So this is what is often used to fine-tune transformers, right? So nobody, except maybe if you're Google or OpenAI, can train from scratch this huge model with I don't know, hundreds of billions of, or even trillions of parameters. So you take a pre-trained model and you perturb the layers with a low rank matrix that is written as an outer product of two seen matrices, right? But now if you look at it, right, so if now this is my representation of so these are my new parameters, right? So the LoRa, I can multiply each of them by some invertible matrix, right? and it cancels out, right? So this is called the general linear group, right? So that's the symmetry that we have in this representation. And of course, you must account for it if you have an architecture that is designed to learn on LoRa's, and basically to say that any such transformation is functionally equivalent. And we have a paper with collaborators with Hagai Maron, who is now at the Technion in Israel, and we have a joint student at Oxford that exploits this direction. And I would say there are many papers in this field already. So this year at AITHYRA, there was the first workshop on weight-based learning, and there are a few researchers that are active in this space. And I think you should invite them to the podcast, and in particular Hagai. Well, he has been a long-term collaborator and friend. I was actually his PhD examiner in Weizmann in 2018, probably, something like this. And since then, we've been working, and he has been a great inspiration for many of the things that we are doing.
Yeah, he's a great researcher, for sure. Okay, do you want to talk a bit about drug designs and how can we do it?
And
Well,
I was just going to say, not everybody on the call may be so familiar with your work too. So if you have any high impact work on this that you want to highlight, please do so now.
yeah, of course. I mean, it's a very broad field, right? And I'm definitely not a biologist or a chemist, so I know about drug design well from what I learned from my collaborators. Roughly speaking, so how drugs work, right? And I'm sorry for biologists that will hear this and will be offended if I'm simplifying it too much, but in most cases, so all the important stuff in our body is mediated by proteins, right? So proteins often we call them the molecules of life, right? So they're encoded in our DNA. So they have, again, these long sequences of amino acids. They fold into different complicated structures. And these structures, basically the structure itself gives the protein its function, right? So it's like pieces of puzzle that stick together and interact. Now, I'm hugely simplifying, right? So in reality, these are quantum mechanical systems, right? And they don't really sit as these kind of rigid blobs. So they also change their conformations, right? And they wiggle a little bit all the time. And of course, they are not just an abstract thing. So they also live in solution, right? So there are some other molecules around them, right? But again, to make it extremely simple, so typically it is assumed, right, that the metaphor for proteins is lock and the key. So same way as you have a unique key that will fit into the particular configuration of knobs in lock, same way a protein will have certain structure, right, on its molecular surface that will recognize only a particular molecule that will bind to it chemically, right? And then some chemical reaction will happen, right? And this is responsible for part of a biological process that is responsible for healthy functioning of cells or maybe for a disease. Now, most of drugs work by the principle of loss of function. So you know that there is some target, some protein that is associated with some disease, and you know that if you block it, right? So if I design a molecule that binds to this protein, then the disease, right? So this whatever chemical machinery will not work anymore and the disease will be cured, right? Again, hugely simplifying, right? So basically some kind of geometric blob, right? So, and you stick something into it, and that's how many drugs work. Now, in many cases, the target protein is what is called undruggable, right? So it's very difficult to design a molecule, and we're talking about small molecules, right? That would fit into some hole in a protein and make it dysfunctional. But you can design another protein. So basically, the drug is a protein molecule itself. So these are called biologics or biological drugs. Often these are antibodies, so special types of proteins for a variety of reasons because, well, the body tends to reject them less. And we have actually very successful drugs of this kind on the market, right? So some of the blockbuster drugs are biological drugs, especially in the oncology domain, in cancer immunotherapy. So basically then the problem of design, right, is how to find a molecule that implements certain function, right? So for example, that it sticks to your target protein. And this is this is actually how I got into these fields. I was approached by Bruno Correa, so he's a biochemist, a structural biologist at EPFL in Lausanne, and he was saying that, well, you work on the three-dimensional shapes, right, and how to do learning on geometric objects. So we have geometric objects, right? So these are proteins. So there is not only geometry, right? So there are also chemically charged surfaces. So there is some extra stuff to it, but we did some of the first works around applying the same stuff that we developed for computer vision and computer graphics applications to these molecular surfaces. So I was at that time I was on sabbatical at Harvard. So he and his postdoc came for a few weeks. So we lived at our place, and we tried to put together this simple prototype, an architecture that would basically understand what makes proteins bind, right? So we have some data that we know which proteins go together, right? We stick together. So we try to learn some rules that will tell us what are the properties of these surfaces that make proteins bind. Now, it was probably beginning of, first of all, a very fruitful collaboration, but also some kind of humbling experience, because the architecture was working within a few weeks, and we could run computational examples. But then to make it convincing to domain experts, it took another couple of years almost. So we had the first paper that actually appeared on the cover of Nature Methods. And then it took another 2 years to do experimental validation to get it into Nature. So people who actually...
What does it mean to make like experimental validation? So like you have a model that now gives you like prediction for a specific protein structure that can be helpful for specific type of like I don't know, solutions, and then you say, okay, so now I'm taking it into the lab and I want to actually to try it on mice or something like that.
Yeah, so the goal is protein design. So you want to design a new protein that binds to some important target. For example, one of the targets that everybody likes is PDL1, so programmed death ligand. So this is used in cancer immunotherapy. So this is roughly the kind of friend or foe mechanism that the cells tell that to our own immune system, don't kill me, I'm a friend, right? And some cancers develop these kind of proteins, right? So you block it and then you allow the immune cells to kill the cells of the tumor. So what it means, the experimental validation, is you actually build this protein in the lab and you test it in different ways. So you can, for example, test whether it really binds, right? And also what binding affinity, right? So this is what distinguishes between something that can be used as a drug or something that is just, well, a lab curiosity. And you also show examples of difficult binders, so to proteins that, for example, have never been drugged before. So one thing that we showed in the Nature paper, experimental validation, was binders for the spike protein of the SARS-CoV-2 virus, so the one that was terrorizing us with the COVID-19 disease. We showed that it binds across different variants of the virus, right? That results in structural changes in the spike protein, and also showed the pseudovirus neutralization. So it was basically a comparison to a commercial drug, an antibody from AstraZeneca. So I'm saying actually it was mostly them doing the experiments. But this is what it takes if you work in this field, if you want to be taken seriously, if you want that these methods are used by domain experts, it's years of work.
So this is very different from, I don't know, deep learning in CS, right? It's like you're doing 3 months project and move to the next one.
It is very different, and I'm trying to push more for doing this kind of work now. Of course, students need to publish in Europe and AITHYRA and ICML, that's what makes them employable. So we try to do both. But these are much longer projects, and in life science, it is easy to finish a PhD with having maybe one paper or something like this, because it takes years to do these experiments.
But do you feel it like it's more meaningful? Like now you're doing a project that like, you know that this is a very good project that actually it has a very strong impact, or you're frustrated from that it takes so much time and like needs so many verifications?
I mean, it's frustrating, right? Because we're, as you're saying, so for us, it takes a few months to produce something that is publishable, but I think it's necessary. So if you work in this field, you must take it one step beyond. And even we are not even talking about in vivo validation, right? So everything that I told you, so this is in vitro, right? So you mentioned mice. We didn't use any mice, right? So that would be another step, another level of complexity, which is necessary, right? If you design real drugs. So I work with biotech companies. So I'm involved in a company called Vant AI. So this is another even more interesting stuff. So this is what is called, so Vant is trying to design molecular glues. So molecular glues, roughly, so these are molecules that induce interaction between proteins that do not normally interact. So when you have two proteins, right, they don't bind, but you can design a molecule that makes these proteins interact. And one of the mechanisms that is used in, well, every cell in our body is there is a natural way of destroying proteins. So there are often misformed proteins inside the cell, so you need to get rid of them. And there is a special mechanism that involves the molecule of ubiquitin. That was actually the two Israeli guys that got the Nobel Prize for it. Basically, you can hijack this mechanism to destroy proteins that you want. So you can target proteins. So it's called targeted protein degradation. And instead of basically loss of functionality, you have a way to rewire the cell. So you can change the way that things work inside the cell, both for designing new drugs, but also for understanding biology, right? So that's how you can perturb and you can modify the functioning of the cell and learn how it works normally. So this is something that we are trying to do at AITHYRA, the new institute I'm in charge of in Vienna. So this is one of the directions that we are looking into.
Okay, I think we out of time. Do you have anything that like anything that you want to say, advertise, some plugging?
Yeah, what didn't we ask you about that we should have asked you about?
Well, you wanted to ask me about the recent papers about parameter efficient optimization, but I guess we touched on this as well.
That's
right?
okay.
So, yeah, well, we do a lot of things, but I don't know. It's I'm interested in AI for science in general. So, and I think maybe societal implications, right? So if you want to take it in these dimensions, so this is probably where we will see a lot of interesting changes, I think, very rapidly. How science, not only what is the role of scientists, right? So it's interesting to think of it maybe from slightly philosophical perspectives. Science, the way that science has been done, didn't really change in the last 400 years, approximately, since the times of Newton. Of course, the technology changed and the instruments that we use have changed dramatically, but it is still 3 stages of you come up with a hypothesis, you use it to make predictions, and then you test it experimentally. And technology has been used with the experimental validation. Newton himself invented a new type of telescope to validate his theory of gravity, right? That he then used to calculate the positions of planets and other celestial bodies. Now, when we had computers, all the prediction is done in simulation, but it's always that the hypothesis generation was a human endeavor. So we had the eureka moment or the spark of genius or whatever you call it. It was always a human scientist that comes up with a hypothesis, and then everything else can be somehow mechanically amplified by a machine, right? Whether it's a computer or whether it's actually an instrument or a device. Now, I think we're seeing for the first time ever in the history of humankind, for sure in the history of science, that the machine is taking maybe still as baby steps, but part in this creative process in hypothesis generation. So we see examples from DeepMind, for example, in solving mathematical problems or some proofs of some theorems. Again, I don't think we have seen anything dramatic and groundbreaking, and I think there is a lot of skepticism, and I think rightly so, right? So can we produce something new that we have not seen before? But I believe that it's not impossible. I think it's actually quite likely to see in the next years, basically generated science. And some people believe that mathematics will be the first field, right? Because if you think of mathematics, it's you have ideal data. There is no noise, right? And also what is good in mathematics is that it might be difficult, for example, to prove a theorem, but it's very easy, right? Or at least relatively easy to validate whether your proof is correct. So it's a little bit like NP-hard problems. So it's difficult
And
to
also
solve.
code.
And also code, of course. Yeah, also code. But code is, I think it's already happening, and this is potentially a multi-trillion industry. So this is actually Terry Tao. So, well, he's a very famous mathematician, a Fields medalist. So he works on AI for math, and his prediction is that it will happen sooner than later. And he also has this interesting concept of experimental pure math, right? Which almost sounds like an oxymoron. But if you think of, I don't know, a machine learning method, whether it's an LLM or maybe in the future will be something else, that produces candidate proofs for a theorem, right? In most cases, it will probably be garbage. But even if it's right once in a billion, then you are done, right? So you can delegate it to just computational power. Of course, there are many questions, right? So how you formalize mathematics so that it can be approachable by machine learning, and there are efforts in this direction, and it's not immediate how to do it automatically, and how you prove interesting things rather than boring nonsense, right? Because formally you can prove theorems, but they will not be interesting, right? And whether the pure mathematicians, right, the purists will consider this as a valid proof, because I think there is an argument even about this, right? And it's not that we didn't have automated proofs before, right? So there was, I think the first result was in the 70s in graph theory, 10,000 pages proof that was generated by computer, but some people say that this is not a proof, right? So that's not what we consider mathematics. So there is also some maybe notion of elegance and beauty that may be a little bit difficult to formalize. but it is probably coming, and it's not clear what will be the role of scientists in this post-theory world, and whether it will be just next level of abstraction. Like in software development, we moved from writing code in assembly and then functional languages and then object-oriented languages, and now we might even write it in plain English, right, with maybe just a few examples, and some AI will generate the code for us and test it for us. And I think there are concerns for the society as well, right? So if we delegate too much of our cognitive skill to the technology, we might unlearn things that make us humans. And throughout our history, we lost a lot of skills that were historically essential for survival, right? So how many people can ride a horse nowadays, right? And just a few centuries ago, if you didn't have this skill, you would just die, right? It was totally necessary for the survival of the civilization. So if we lose some of skills, cognitive skills that make us humans, it's not clear what kind of world it will be. But yeah, this is probably a little bit going too far.
I think then it's very interesting because like for different problems, it's not that like now people are talking about AGI and things like that, right? That will like, when will be the time that we will achieve AGI? I think for different problems, we will have different timescales, right? And we need different calculations and different milestones.
Yeah, and it's not AGI, right? So a machine learning model that can prove mathematical theorems, whether it's general intelligence, probably not, right? So you can maybe call it superhuman intelligence, but it is useful for this particular field, and it can make human scientists in this field obsolete.
Yeah. So we will still have a job in the next at least few years, right?
There was an interesting paper from Microsoft, I think, and they ranked the risk of different jobs to be replaced by AI. So it's interesting that actually a job like mathematician was very close to the top of the list in terms of being at risk. And what is not at risk is a job like a plumber or a phlebotomist, right? So I think we need to change our professions.
I joke, I agree with this, but tactile physical simulation is what's keeping physical robots from being good, and that's possible to solve for one. But for two, LLMs, they need to solve tokenization in some way before math, because yeah, I'm aware of these like new results coming out about like math performance on these Olympiads is doing super well, but they're unreliable for usage like a calculator. And I think the majority of, sure, math experts like Terrace Tao, who you mentioned, probably understand this, but the general public doesn't. And so they, ask it to calculate.
But it's the wrong tool, right? So how good are you calculating, right? So if I ask you to multiply...
I do know how to... Well, okay, so then
mentally,
what you're saying is, okay, well, the AI is going to write the code to do the calculation correctly, to which I'm like, okay, that's fine too, because yes, I have to go do the arithmetic myself.
No, the AI will use a different tool as the same way as we use a calculator, right, to multiply numbers, because we cannot do something more than 3 digits in our head. So same way it will probably need to work as us, right? And it's unfair to ask a model that is designed for completely different tasks to do these sort of things.
Well, I agree with you, but when we say that these models are so good at math, I really worry that the general public assumes they hear, oh, these models are replacing mathematicians, and then they run it, and let's say the disabled tool use or something, and then it's like, why does the model unable to add numbers together, right? I agree with this. I just think that math...
I know many mathematicians, very prominent mathematicians, that would not be able to multiply numbers correctly.
Okay, you're right. That's fair, I guess. I suppose poetry is a better example of this, where there aren't good tools to automatically like rhyme. And the fact that actually rhyming is pretty good now in these models is uniquely, especially interesting, because there's no concept of like syllable counting or anything of that like in the tokenizer, right? So
poetry is I used to even translate poetry when I had more time and was younger. It is difficult, so I don't think that we are anywhere close. So if you ask something very specific, right, and translation is actually a good example, because you want to preserve the meter, you want to preserve the rhyme, obviously, you want to preserve the sense. you also want to preserve sometimes, I don't know, metaphors, right? And the special poetic language. And sometimes it's near impossible. So there are some, for example, poetic styles that work well in one language and do not work in another language, right? So, and I don't know, if you take Goethe, for example, and you try to translate the whatever 20 something plus meters and different rhymes forms that he uses in Faust. And for example, when he translates the Greek hexameter and try to translate it to French, it will not work. And most of the LLMs, even the most advanced versions. So this is how I test whatever ChatGPT 5 or the next version. It still does a very poor job.
And do you think it's possible? Do you think it's possible, like, to train them to have a good, like, translator for poetry?
I think it is possible, right? So it's a general purpose model. So I think expecting from it to be able to translate poetry is not necessarily the right expectation. But yeah, I think if you train a model particularly for this task, it can probably work better than humans. I don't know if there is something special in poetry that is a human touch, and maybe what is written by these models still lacks, I don't know, the soul of a human poet. This is something that is very difficult to quantify.
Yeah, but I think, like, it's also, I don't know, for example, human engagement, right? Like, in principle, I would assume that, like, it will be a very easy task for models, right? Like, how to increase human, like, to make, like, in social media, I don't know, likes or something like that, to increase the number of engagement. But
yeah, to write text, right, or to generate an image that is appealing to
Yeah,
basically that optimizes this metric. But you can also measure. So there are studies that try to understand the brain response, right? So you can measure actually what happens in the human brain when a person listens to a piece of music or reads a text or sees an image, and basically it's some kind of emotional perception of or emotional response to an input, something that can be quantified and then optimized for it. So I'm pretty sure that even though we like to think of ourselves as some kind of unique paragon of animals, right? So that's how Shakespeare, I think, put it. We are probably very predictable.
Yeah, it's a good question. Okay. Do you have anything that you want to add?
No, I think we've been almost 2 hours.
Ellen?
No, it's been a real pleasure to have you and pick your brain. Yeah, hopefully sometime in the future we'll have you on again. Really, anytime.
Yeah.
Well, invite some other people. So invite some of my former students. I think Federico would be great to talk about, and he can also maybe say a few more things about what he's working on at DeepMind now. Yep.
We will. So yeah, thank you, Ellen, and thank you, Michael, and thank you for all the people that are listening to the episode. See you next week.
Thanks, guys.